Reliability programs. When it comes to managing reliability in a mill or facility, there can be many kinds of programs. Reactive, run to failure. A facility may have as many as 5,000 operating motors. Not all are as critical as others. We cannot possibly perform annual testing of all 5,000 motors. Normally, we are just not budgeted or staffed to facilitate that. So yes, some motors are not tested. These motors should be installed properly, kept clean and operated within ratings so that these too have a long service life. Preventive program, a pre-planned periodic motor replacement. Some applications have environments or operations that are more damaging to the motor's health, so these are simply removed on a time basis. It's important what is done to these motors. I believe if the motor does not pass both LV and HV testing, the motors should be rewound and all connections sealed so that future testing will be successful. If we always only recondition, we will be filling our spare storeroom up with 3 and 5 year motors rather than 20-year motors. Predictive program, where testing and winding status determines what we do. It is a complete program where static as well as dynamic testing is performed. The dynamic testing that I feel is necessary is vibration. Low voltage, high voltage, and vibration give us the information that we need to evaluate the stator and rotor winding integrity, and if compromised, we should schedule the motor to be replaced. Factors that influence motor failure. Here is a curve that represents the failure probability of any motor. Initially, when a motor is manufactured or repaired and then installed, there is a period in which the probability of failure is high. Some reasons for this is the possibility of any manufacturing defects, shipping damage, storage degradation, as well as installation problems. After operation for some period, that probably will decrease and remain low throughout the life expectancy of the motor. At the end of life, the probability of failure again increases. This region is called the end-of-life region of the motor's insulation system. We want to be able to identify a motor that has entered this region and replace it prior to it failing while in service. A motor that fails in service costs us unexpected downtime as well as possible severe damage during the fault. Both correspond to dollars lost. Another way of looking at the life expectancy of the motor is this trend of the expected dielectric strength of the winding insulation. Dielectric strength of insulation refers to what voltage will the insulation withstand before failing. When new, the insulation system is new, the voltage required to break down the insulation is very high, many thousands of volts. As long as the motor is operated within rating, the breakdown voltage remains very high until through natural degradation the breakdown voltage begins to decrease. When the breakdown voltage reaches the voltage level that the motor sees during operation, the insulation will fail, and the motor will have to be replaced. Again, we want to find the degradation well ahead of reaching these lower levels. We want to find it up here in the nose of the curve. This is why high voltage testing is necessary rather than only using low voltage. Low voltage testing is considered at or below bus voltage that supplies the motor. Where do motors fail? I've seen many studies that agree very closely with these statistics. IEEE performed this study. Bearings 44%, rotor 8%, stator windings 26%, and other was 22%. So, if we understand this, we can reduce our unexpected motor failures in a mill by almost 30% by simply performing effective motor testing. A factor that influences motor life is thermal aging. When a motor's temperature exceeds its rated insulation temperature, it can have detrimental effects on the motor's performance and lifespan. The insulation materials used in motors have temperature limits. Exceeding these limits, even for short durations, can accelerate the aging process of the insulation. A rule of thumb is that for every 10 degrees Celsius increase in temperature, the rate of degradation is doubled. Conversely, for every 10 degrees Celsius cooler, the insulation life is doubled. Some people feel this doubling effect has been proven inaccurate. However, we can accurately say an increase in temperature negatively impacts the lifespan of the insulation. Another factor is the effects of contamination building onto the windings. Chemicals that are deposited onto the insulation attacks the insulation. This also builds layers that thermally insulate the insulation, causing heating of the windings. Contamination and moisture lead to tracking along the surface of the conductor. Any exposed copper part can track to ground in this fashion, which bypasses the insulation. This creates problems when attempting to measure the resistance of the insulation when it is bypassed from surface leakage caused by contamination. Another factor is mechanical. During starting stress, the winding could move. This movement degrades the insulation. Thermal growth is another means for mechanical erosion of the insulation. And finally, overvoltage. Overvoltage is a major cause for insulation failure. Insulation will be electrically stressed during high voltage events. There are several sources for high voltage stress. Some include lightning, operating on a variable frequency drive with fast switching components such as IGBTs, and what we call switching. Switching is the act of starting and stopping the motor. During these events, voltage spikes as high as 4 times bus voltage can be felt on the windings. Static LV and HV testing will actually serve to quantify these effects. Anytime current flows through windings in a motor, resistance in the wire, as well as other losses, cause heat to be generated. One of the key components affected by this heat is the insulation system of the motor windings. How much heating can insulation withstand? NEMA MG1 is the standard for information concerning performance, safety, testing, construction, and manufacture of alternating current and direct current motors and generators. NEMA MG1 standard establishes 4 classes of motor insulation. Each class defines the insulation system's ability to endure a specified temperature while providing a specific operating life, temperature rating. Major and most commonly used motor insulation classes include A, B, F and H. Understanding the differing insulation classes and limitations for each is an essential part of an effective reliability program. Operating motors within the design parameters of their insulation class can yield significantly increased reliability and motor longevity. Class A rating is 105 C, Class B is 130 C, Class F is 155 C and Class H is 180 C. The maximum permissible winding temperature rating includes 3 elements. The ambient temperature, the allowable temperature rise when operating, and a hotspot element that must be included for areas that may be heating more. Class B motor insulation maximum permissible winding temperature of 130 degrees Celsius consists of ambient temperature of 40 C, allowable temperature rise of 80 degrees Celsius, and allowed hotspot over temperature of 10 degrees Celsius. Class F motor insulation maximum permissible winding temperature of 155 degrees Celsius consists of ambient temperature of 40 C, allowable temperature rise of 105 degrees Celsius, and allowed hotspot over temperature of 10 degrees Celsius. This class consists of dielectric materials like mica, asbestos, and glass fiber. Class H motor insulation maximum permissible winding temperature of 180 degrees Celsius consists of ambient temperature of 40 C, allowable temperature rise of 125 degrees Celsius, and allowed hotspot over temperature of 15 degrees Celsius. This type of dielectric material consists of silicon elastomers combined with glass fiber. The majority of all motors are designed for a 40 C ambient and an 80 C rise at 1.0 service factor, aka full load. Motors rated with a 1.15 SF can be overloaded by 15%. With the typical motor design and operating at full service factor, the temp rise is 105 C. Therefore, When operating the motor at 1.0 service factor, the winding temperature is 130 C, and operating at 1.15 service factor, the winding temperature is 155 C. Which means when operating at 1.15 service factor, you are at the Class F insulation system maximum permissible temperature rating. This results in a 3-year life expectancy of the winding. A motor's insulation should have a relatively high temperature capability and a relatively lower operating temperature. This provides for thermal margins in the event of motor overload, severe starting duty, safety margin. So, a motor designed at Class B insulation limit can have Class F insulation. This give a margin from motor operating at full load temperature and insulation temperature rating. Is it okay to continuously operate in the service factor? This is what MG1 says: all motors shall be rated for continuous duty, S1 for IEC motors, and shall be designed with a 1.15 service factor but shall operate normally at 1.0 service factor or less. Operating above the 1.0 service factor should be limited to intermittent periods of time without damage during unforeseen circumstances. If base loads above 1.0 service factor are expected as a frequent condition, the next power rating should be used. Service factor is included in the motor rating for power quality issues and not for continuously operating above the motor HP rating. This graph indicates the relationship of insulation life expectancy and temperature. Each curve is a different insulation class. This graph is based on the idea that for every 10 degrees Celsius increase in temperature, the rate of degradation is doubled. Whether the half-life rule is entirely accurate or not, maintenance experts do agree that excessive heat will cause rapid deterioration of the winding insulation within motors. First, let's examine the curve for the Class F insulation. We said that most all motors are designed for a 40 C ambient and an 80 C rise at 1.0 service factor, aka full load. Operating the motor at 120 degree correlates with life expectancy of 250,000 hours or 28.5 years. If temperature is increased to 130 degrees Celsius, this curve indicates a 50% decrease in motor life, 125,000 hours. When operated at maximum Class F temperature rating, 155 degrees Celsius, the motor life drops to 20,000 to 25,000 hours. Approximately 3 years. A 3% voltage imbalance will cause a 18 to 20% current imbalance and a 25% increase in motor heating. This condition is not sustainable and will eventually lead to iron overheating and a significant rise in motor temperature that, as mentioned above, may not be detected by the thermal protection. Motors operating with current imbalance must be derated. Derating is the operation of a motor at less than its rated maximum capability to prolong its life.